Ok, estamos ao vivo novamente. Já. Tá. Ok. Vou só cortar o nosso áudio aqui.
Not anywhere near a target condition. This is important to understand. Okay? So next slide. Now, the community thinks purely in going in this direction. Purely. Okay? So if you're looking at those very early times, particularly those that failed immediately, they're viewing that they are all examples of stress rupture. They all follow that power law of Bob. That is their fundamental assumption, and you do not question that assumption. Unfortunately, I did. So far, so good? Because I know enough about the problem that in order to have a true stress rupture test, it's measuring ability to hold a constant load. You have to get to that load. If you do not have the tensile strength to support the load, it's a reject. You've never got any information. I knew that. Okay? So, ramp failures, if you look at it as they literally think in terms, they used to do the test, you would have the weight and there would be a stand. Kick the stand out. It's immediately at load. No, it's not. The load has to be established. You got to stretch out the cord. It may not be much, but it has to be stretched out. This is a fundamental issue. And some of them don't ever, they just, boom, they fall immediately. Got the idea? It's even worse than that. With kick the stand out, you create vibration. Vibration are cycles. That's not a constant load. The original origin of this TW, this is a window, was to see if it was stable from any cyclic vibration. Vibration is a different failure mechanism. Tensile strength is a different failure mechanism. They are assuming that this is exactly the stress rupture failure mechanism, all the way back. But they recognize they don't have the time correct. So what they then say is, oh, we will left censor any item in this window. So far, so good? There are very strict rules for left censoring, very strict. This community doesn't understand any of that. They do it as a convenience. Because there's strong assumptions associated with left censoring, and left censoring is controversial even in biostatistics. Because you are assuming that whatever is happening on this side explains that side. This notion of the convergence between coming up and being at constant load is fundamental to understanding the issues. My poor friend, the reliability engineer, has no clue, none, zero. Okay? So far, so good? Okay? And notice I have effective time here. The community likes to replace the actual data with distortions of the data. And I emphasize that word because once you understand what they're doing, this is a distortion of the data, and it is a problem. The data are the facts. What's the one thing you don't disturb? You know, you can check for outliers. Does it make sense? They do something much worse than that, and they don't realize it. They think it's innocent. So far, so good? Okay? So this is where we're coming. And in fact, my friend will censor valid data. You don't censor valid data. He says, oh, it's too close to zero, so I don't know what it really is. No, you know, we know exactly what it is. We measured it precisely. Are you seeing some of the conversations we have? Rule number one as a statistician, the data real rule, right? If they're outliers, you go investigate them, but you don't willy-nilly adjust them. Okay, that's major. You're in trouble at that point because you've got to justify that in many, many ways. Next slide. In our particular case, we actually had a ramp process. We had it under a clamp and we pulled it. We applied a load and we can measure it precisely. It was not an instantaneous load. It was going at 40 stress rupture units per hour. So the time to get it from 0 to one of the target loads was between 2 and 2.25 minutes. We had very good information on it. So far, so good? No basis for left censoring. Left censoring is for missing data. No missing data. Point number one. Point number two, the purpose of the ramp is not about time. It's about getting it to the load. That's the sole purpose for it. We don't care how long it takes to get up there as long as it's reasonably consistent. All I'm interested in is the load. I can, however, calculate the time and we do it by a standard ramp rate. That load has all sorts of interesting features in it. So measuring the time is not accurate. Measuring the load is perfectly accurate. That's what the equipment is designed to do. So we didn't really measure the time. The clock was running, but when we created a time, it was a standardized time in a perfect relationship with the load. The load is the focus of the ramp. Get it to load. That's the fundamental point. That's exactly what we do with a tensile strength test. That's what we do with the strength test. This area here is best modeled by a 2-parameter Weibull distribution, the one we talked about in the first lecture. This is well modeled by the 3-parameter Weibull distribution. Now we're beginning to get into the real statistical issues. Something you don't see in a textbook. How do you combine two aspects of a profile? It's just basic probability theory. It's no rocket science, but we never teach it. That also leads to issues. So far, so good? Okay, next slide, please. This is the actual picture of the loading process. What we're measuring are the loads, and we can come back and calculate the times by dividing that by the ramp rate. Those times are calculated. They were not the observed times. Point one. Secondly, if we measure time from time on hold, This is negative time. Did you hear me? My engineer friend had no problem with using negative time for a Weibull distribution. Now, for a Weibull distribution, you know, unless you've got that threshold parameter, the values for your characteristic have to be positive. Oh my, he seriously was talking about negative time. I said, James, you can't do that. Oh, I'm doing it. I said, no, you can't. This is not an uncommon conversation with my friend. Please understand the statistical literacy with this community. It's not high. Okay? The color coding is consistent, so blue is always going to be that lowest stress ratio. Red will be the middle. Orange is the top stress ratio level. Okay. Any questions? But I think we're fine. So once again, to emphasize what's happening here. This is the basic log of the survivor function. This is the key to the linear model for this segment of the curve, this part. But the ramp behavior is a two-parameter Weibull distribution. Its characteristic of interest is below. The whole purpose is just to get this up to this low. We don't care about that time. It's just my friend worries about that time. Okay? So far, so good? One of the hardest parts of the conversation I'm having within NASA, what do you mean by time? Okay? So far, so good? What happens if you put a constraint on the three parameters so that then they can model precisely a two-parameter system? What have you just done with those three parameters? Are they three independent parameters anymore? No. They're effectively two. Hold the thought. Okay? Next slide, please. Here is the basic structure of the model. This is from last time. So when we start talking about the classic stress rupture, the power law parameters, just keep in mind, T rep is a y-intercept, basically. Rho is the negative of a slope, so this is the actual slope for this curve. I'm connecting the log of the characteristic times for each one of the stress ratios. Beta is just the spread given the stress ratio. They are three distinct independent parameters for one another. We cannot, a big no-no is to have a formal relationship, a precise relationship behind the linear model portion, the deterministic portion, and then beta. Think about how we model normally distributed data. I can have a model for the mean of the response. I can have a model for the variance. I've done a lot of that. But you can't have the mean be a predictor of the variance for a normal distribution. So far, so good? Nor can you do it in a Weibull distribution. It's a major no-no. Okay? Goes back to the definition of the model parameters. We're not dealing with a binomial where the mean is dictating both the mean and the variance. That's the nature of our distribution. Next slide. Now I have added the ramp data to that picture. The ramp data looks like it has a slope. It does have a slope. And because I have a perfect relationship between the load at which it failed and the time, that load is ramp times time. So that slope turns out to be 1 of necessity. So far, so good? Now, you talk to engineers and you talk about a classic stress rupture model, they understand rho as a slope. They understand it as a slope. But they don't understand that in this particular plot, they're not one slope. There's not just one. There are two. A different slope for the ramp, because the way we're doing it by the pull, versus the slope here, which is helping to explain the change in the probability of failure depending upon the stress ratio you're using. Two different things. Okay? Welcome to my world. Now, what do we mean by time? For ramp failures, if I talk about the time on test, I can use the calculated time. In this particular case, it would be starting in, this is negative time. Oh, no, this is time on test, I corrected it. So I started at 0, and here, whatever was its ramp time is the test time for the ramp. For the hold failures, it's up to the load, and then you add that to the hold time. It has nothing to do with how we're going to model that. That's a fundamental problem here. Okay? The confusion of time on hold for time on test drives the conversation with this community. It's a fundamental problem. Now, it becomes interesting how to resolve that. Next slide, please. I can't emphasize it enough. The load process is just to get it to load. Time is not the issue, it's the load. That's the characteristic of interest. I can frame all the probability arguments in terms of load. Time is a convenience, but load is the actual characteristic of interest. On the other hand, with the hold process, the characteristic of interest is the time on hold. The time on ramp is irrelevant. Fundamental. So far, so good? Okay. Now, let's go back to this picture. My stress rupture engineer is looking at it from this perspective. It's coming back to here. And as far as he's concerned, I've left a little gap. There's the gap where the ramp occurs. He's assuming that it's all one failure mechanism. It's all stress rupture. And prior to this study, no one took a look at what's happening here. No one. So as a result, people actually thought they could do things like effective time. They could left censor. They claimed it had some time there that they couldn't observe. So they felt very comfortable left censoring. They became very comfortable about creating all sorts of new things. But it was always from the perspective of coming back to 0. They never thought about what's happening as I go up to the target condition. So for my engineer friend, the time on test has to be time on hold. Even if I can't observe it, I'm going to create something for it. And what happens when you create data? You had better be able to document thoroughly that that makes any sense. So far, so good? Because the data are the facts. Oh, in our experiment, we have the data for everything. Am I getting my picture across? Okay? So my engineer friend says, we always analyze the data this way. And I say, you've never had data where you do where everything is. We have the value for everything. Okay? So in our test, we can separate out time on ramp, time on hold, and create a time on test, but it's irrelevant. For my engineering friend, it's important. Okay, next slide. I talked about this, the kick out the stand. Things seemed to fail immediately. There was no ability to measure that time precisely, so it is a complete unknown. The assumption coming back to the left is that it must have been at the load condition, so they assume a very small time and censor. They have no good basis for that small time. They make it up. Wind's blowing this direction, it's 0.0001. Tomorrow it could be 0.01. So far, so good? Small number. You got a lot of them. That's a big bias. Okay. Now, it assumes same failure mechanism. What the community doesn't understand is that that assumption that it's the same failure mechanism is testable. This community assumes its model is God's model. It is true. If they can estimate the model, that must be the truth. My friend has said, sometimes you must torture the data to get it to estimate the model. Torture. What is he doing? He's distorting the data. That's an ethics violation they don't understand because they say the community allows them to do it. So far, so good? Okay? It's well intentioned. It is the tradition to give it a small value, but even that is not proper. So far, so good? Okay? He planned the perfect experiment. He wants to disown it then. Next slide. The current recommendation in the community is to replace the observed times with equivalent times. This has been around for about 50 years. It is the gospel in this community. I hope you now appreciate the difficulties I'm dealing with. We have a community of engineers who have created an ad hoc analysis, and they don't understand the basics of basic distribution theory. The one-eyed person is the crown in a blind society, okay? I'm dealing with NASA's stress rupture subject matter expert who knows absolutely nothing about how to analyze data. But he understands perfectly how his community analyzes the data. Are we understanding one? Okay. This paper is a pain to read. It's poorly written and should be retracted. Okay? It's fascinating, but it explains the critical insights. Great read for me. They explicitly assume the same failure mechanism. Just to give you a quick overview of why I say it should have been retracted. They go in and they take a 3-parameter stress rupture classic power law and say, well, I've got a ramp, so I'm going to force it to look like the ramp. So far, so good? And I'll show you how they did that. I'm not going to go into all the math details, but I'll show you how they did that. And then they tried to look at the result of that. There were 3 derivatives they took, set them equal to 0. They could solve for 2, but not for 3. Now, is that a clue that there might be a problem? And the one they couldn't solve for was that rho parameter, the slope. So they waved their hands saying, oh, in theory, there's an answer, okay? And it's a real problem if it's 0. So far, so good? But we can't get it. So they then do every example they have with assuming that beta, the shape parameter, is 1, which is an exponential distribution. Oh, not. They just took that classic stress rupture model. The parameters are rho, this is beta. Beta, rho, and beta. Beta equals to 1. It's no longer a Weibull distribution, it's an exponential distribution, which has how many parameters? 2. They make a statement in the paper. Oh, if you can't get this derivative to work, then obviously it must not be the same failure mechanism. Hello, what is the proper answer? You came up with a great solution for showing that it can't possibly be a correct solution because of necessity that rho parameter, when you map it down to 2 parameters, has to be 0. Okay? That would have been a clue. Reviewer should have picked that up. It was in a good journal, but it's mixed because it depends if it's engineers reviewing it or statisticians. So far, so good? But I'm going to show you what they did. So they assume the same failure mechanism. They're trying to explain the 2-parameter ramp load behavior by 3. The ramp is a linear profile, so they integrate the stress over the ramp. They assume a linear stress. So R is the ramp rate, T is the time. So far, so good? So the stress at any point on the ramp is equal to RT. Next slide, please. This alpha T is just how the deterministic part, what I've been calling eta, is changing. So this is just saying how eta, the characteristic time, changes. This is the classic Powerball. They integrate that, and then they get this crazy result like here. So far, so good? And you can trust me on this, and this comes directly from the paper. So this is how you can map the 3 stress rupture parameters to model the 2 ramp parameters. Okay? And the math is correct. But this is just a mathematical exercise. There's no science, no engineering to support it. It's all assuming it's the same failure mechanism. But there's no empirical science to suggest that's true. It's pure conjecture. It's a theory. Next slide. Now, with some algebra, that characteristic life and which would be the scale parameter for the 2-parameter Weibull. Alpha is the shape parameter for that 2-parameter. They get this result. And this relationship is fundamental to everything the community does. Everything. But it's stronger than that relationship here because this is the shape parameter for the strength test. It's a very specific value they have. So they're going to claim that the beta, the rho that they see from a stress rupture is going to map perfectly to the scale parameter of the strength test. That's their claim. And they're serious about that claim. Not that it's close, but that it is exactly equal to. And there are all sorts of problems that come about from that. We'll talk about. Are we okay? Now look at this. Beta and alpha for that 2-parameter distribution have to be unique. They have to be. Maximum likelihood estimators are unique, right? Nope. I got a row here. I got a row here. I change the row. I change beta and alpha, and they're no longer unique. They're unique if and only if rho equals to 0. And at that point, you no longer have a 3-parameter Weibull distribution, you have 2. And it winds up then mapping precisely to that strength distribution. You have constrained your stress rupture model, the power law model, such that it's no longer powerful. Somehow they think it's magic. That, oh, it's 2-parameter for the ramp, but it's really 3-parameter. That's not how they framed it. They framed this as a formal constraint. I will deal with the close enough issue a little later in this lecture. Are we getting the idea? Okay. Next slide, please. They ignore that problem, so then they'll claim that the effective time is the ramp time divided by rho plus 1. Now, everything that my friend does is circular. I know the times, I don't know rho. So how can I adjust the time by something I've got to use the time for to estimate? That's a violation of basic probability distributions. It's not going to be a valid random variable. That's where we run into problems. They build distribution functions in terms of what they call an effective time distribution, but the data that you're using have to go into estimating that particular parameter by definition. Okay? This is not an iterative solution process. It's defining a new random variable. It's a brand new random variable, which is T ram over rho plus 1, where rho is not known. Okay? This is not something like in generalized linear models. This is actually changing the data. And we see the consequences. In the write-up, I show some of the formal proofs why that can't work for the Weibull distribution. I'm not going to go into them today. But that's what they'll claim. And then they'll use that as the basis for doing maximum likelihood estimates. They wind up being highly biased. So we're going to look at this approach, and we'll look at the consequences from assuming that approach. We're going to see how well it predicts the data, how well it explains the data. I'm going to fix it, show it at its best light, and show you still can't explain the data well. And this becomes kind of fun. Next slide, please. The problem is if that constraint is true on both sides, and that's what they literally are saying, the constraint is not here, just here, but on both sides. They really have mapped this way. That's what my friend is truly claiming. Then of necessity, we can't estimate rho. Rho would be 0. That's the yin and shin result. They could not estimate rho because of necessity, how they did it. They mapped the 3 to 2, didn't realize the consequence. So that's much fun. Next slide. Correct analysis is straightforward. I can construct a Weibull distribution right there. So far, so good. 2 parameters. Then I can make a conditional probability argument. It only gets to hold if it survives. So far, so good. Okay. So then, if I look at the overall, I look at the probabilities. I've got A is the event. I'm going to say A event survives, ramp. A complement is it fails. I'll have B is the event survives hold. Note that B is equal to the intersection of A with B. Of necessity, the only way I can survive the hold is if I survive the ramp. So far, so good? So I can make conditional probability arguments, and it turns out I have complete flexibility. So as long as I'm doing this correctly, and I've illustrated it in the text, what I can do is I can build one model right here. I have to keep the survivor probability. I've got to estimate this model, assuming censorship, where I can get a real probability of survival. So far, so good? With that, then I can construct a proper overall distribution, but it turns out to be very simple. I have a classic 2-parameter model for the ramp. I have the classic 3-parameter model on the whole. The difference is the number of observations. In the phase B study, there's 730 observations to estimate that model. So far, so good? However, I lost 22 on the ramp, therefore I have 708 to estimate that model. It works perfectly well. I can do this all in Minitab. I can get the overall likelihood function by just adding the 2 likelihoods. The theory is very simple. We don't teach this in the textbook, but frankly, if I were to teach a math stack course, I would make this a required problem. Make you think about this. It's very straightforward. Key, what's the probability we survive the ramp? So now I've got the ability to test the community's claims. Next slide, please. I'm going to compare it to left center. And I'm actually going to do this in a way that favors the method the most. It's not exactly what my engineer would want to do. It would perform even worse. So I'm going to fit the separate models of ramp and hold. I'm right censoring all ramp survivors. It's very straightforward to show that the overall likelihood is the sum of the 2. It's going back to the random selection of the experimental units. The engineer's analysis defined a 2-minute window. He left censors all the ramp failures. There are 22 of those. He left censors any valid data within the window. There are 5 of those. You never censor valid data, by the way. He is not adjusting by equivalent time, although that's what he says he really wants to do. If he did, it would perform worse, if that's imaginable. Next slide. I cannot show you the parameter estimates. I wish that I could. But these are the actual results. for comparison to help understand how bad these numbers are. This is the proper approach, the rigorous approach based off of conditional probability. Here's the mother model. The mother model is fitting 2-parameter Weibull models to the ramp and to each individual stress rupture. That's the largest possible model. It's the proper model in which to compare. Notice almost no difference in the overall log likelihood. The mother model is slightly better, but not enough to justify the extra parameters. Oh, I thought I had a version where I had the p-value. The p-value on the additional parameters is 0.7 something. So there's no evidence to suggest we need the extra 3 parameters. We got the log likelihood statistics. The AIC, we see a very strong advantage to the rigorous versus the mother model. This is how it broke out into the individual components. I didn't break out the individual components for the mother. Bottom line is the classic model, okay, for stress rupture, where I just dropped all the observations that failed on ramp. Got the picture? That's all I did. Drop the values that they didn't survive. I dropped them. Okay? This model is ultimately statistically superior to the mother model. Now look at comparisons to less sensitive. P-value in R. How often do you see a p-value in R go to 0? They said 0. I've seen 10 to the minus 67. I've seen 10 to the minus 68. I saw 0 on this one. Didn't work. So far, so good. The reliability engineer says the left censored is the only way we should do this. Why? It's his theory. He doesn't understand scientific method. How does scientific method work? You make a guess. You build a theory. You calculate the consequences of that theory. You develop a test. You get the data. And if the data contradicts your theory is bingo. It's just wrong. It's factually incorrect. It's not insulting to say your theory is wrong because the data, if the p-value is 0, your theory is wrong. Stop saying it. Got the idea? Okay? We're at that extreme level. He still insists what he's doing is the proper way to do it. Everything I'm doing is wrong. He can't explain it from data analysis because he doesn't understand it. Okay? He claims he has the science to support it. We just did the science. See my point? We conducted the experiment. And he cannot explain the data with his theory. There's a theory that explains it very simple. It's 2 different failure mechanisms, and it's straightforward. Got the idea? I've got the science, I've got the engineering insight, I've got the data to say what he's doing is factually incorrect. He refuses to accept that. It's fascinating. Next slide. Now, I wanted to have a really interesting comparison because I understand the way to interpret what the community wants to do. One way to view it is I'm not going to impose this constraint for both sides. Okay, that's what Yin and Yang did. I'm not going to impose it on both sides. I'm going to say that it really is 3 parameters, but I'm going to try to force the choice of those 3 parameters to explain as well as they can the ramp behavior. It's with probability 0 that you can come up with estimates of the 3 parameters that precisely estimate the 2-parameter distribution, but it can be close. Fair enough? And that's what my friend will say. Oh, well, I'm really not saying that that's exactly what the says. It's exactly like that. And then he says, well, it's close enough. He contradicts himself on a regular basis. It's okay. This is part of who he is. But what we're doing is adjusting the parameters so that they explain the ramp data. But in the process, you're hurting yourself explaining the ramp. If you can explain the ramp really, really well, you're going to hurt yourself a whole lot in the hole. And the better you explain the hole, the more you're going to hurt yourself with the ramp. You can't do them simultaneously. It would be a miracle. Okay? So we did this. I've shown them the math for this. This helps explain why his effective time Weibull distribution isn't a true distribution. Let's go to the comparison. Next slide. Live Censored's out of the ballpark. So far, so good? It's gone. But I'll put it here for comparison. Notice this is getting a whole lot more interesting. But look at the p-value. Yeah, what's our normal cutoff? 0.05? It's even -7. It's still not right. But it's not 0 anymore. It's just close to 0. Look at the AIC values, massive difference. Am I getting my picture across? Even by going back to the intent of what the community wants to do, the data reject. Well, this was me being as fair as I could be to the community. Okay, is it close enough? I know you can't do it precisely. Is it close enough? The answer is no. Now, what's fascinating to me? What's fascinating to me is that I can actually go in and evaluate now how well it fits the individual portions. That's the beauty of how I set this up. That conditional probability argument allows me to compare it. And notice the p-value for using effective time to model the ramp, it's still, we would reject it, but it's better. But again, we look at the fact that you're got to deal with the issues. You're expending energy on estimating something poorly that you estimate a little better here. But if you did it properly, you've got much better estimates. So far, so good. Next slide. Now I want you to understand what's really going on. So here are some plots. What I've done is I've computed the CDF for the phase B ramp data. So I have got a distribution for the ramp. I censored it, but so I've got actual points and then I've calculated points. It's just a plot of a graph. Notice the probability of failure. This is the cumulative distribution function for the black, and the black is the proper distribution, is much higher than for the gray. What that's saying is that even the best estimates of the community's model under-predicts the failures on the ramp. One reason why the ramp is a wear-out mechanism. The initial phases of the hold are infant mortality, radically different failure mechanisms. And as a result, if you assume infant mortality, you're going to under-predict the actual number of failures for that part of the curve. So far, so good? Okay, that's what that plot is showing us. Next plot, please. This is a little bit of a mess because I wanted to show the distinction between 0.9 stress ratio, highest stress, medium stress, and low stress. That's all I'm showing there. Okay, they don't really overlap each other. Fair enough, but I don't know which one is proper and which one is the effective time. So far, so good? Okay. So next slide, please. Here, I'm using the gray and the black again. So I wanted to see, help you recognize, this is what's going on for a stress ratio of 0.9. This is the ratio for what's going on at a stress ratio of 0.85. Notice initially, it's way over estimated the probability of failure, the effective time. Why? You see, when we look at this probability distribution function, we look at this CDF. And we come to this junction point. It's got to connect. The distribution has to be continuous. If it's not continuous, you got a problem. See what I'm saying? And that's the reason why looking at limits make a whole lot of sense. So when you see this, then it begins to make complete sense. In the whole, you're being penalized. You know, your parameters are being penalized because you under-predicted the failures for the ramp. So now you're over-predicting because there were only so many failures. Okay? There were 48 failures out of those 708. We're seeing the trade-offs here. Next slide, please. This is where I combine it. Okay. So this is now in total time of test. You can see that in the ramp behavior, total time of test, it's minuscule. You actually see the gray as being under-predicted. It's hard to see it. That's the reason for the other plots. But if we look overall, the dominant is what's going on with the whole. It's the dominant amount of time. And the black is not estimating the data well. Okay? That's the key. That's the key. Last slide. I think it's last slide. I remember the first meeting with the team, it was in Blacksburg. It was like 2008, 2009. At the very first meeting with the team, when they were discussing it with me, I understood that what was happening in the early phases was a mixture of failure mechanisms and that a conditional probability approach would make the most sense. I told them that. And in fact, in the early phases of the planning of the experiment, we did everything with that conditional probability approach. I won the day. Okay? Now, there was a long, strange journey in between. A grad student that I hired to work on this project found the yin and shing paper, which supported the engineer's contention that there was effective time. This was a published paper in a reputable journal. It was a pain to read. I trusted the grad student. We just let it go. I knew from the beginning left censoring was naive, but this notion of effective time suddenly had some support there. What do you do as an academic? You have a choice of either disproving it or just going ahead and going with it. And that's what the community has done, it's just gone with it. There are two aspects of the study I'm not able to talk to y'all about just because of time. One is a proof study. The idea of proof is if you take something up to a very high level for just a few minutes and then use it at the use condition, it should last much longer. What have you done? If nothing else, you've eliminated the bad units. Fair enough? That's proof. There are theories in the stress rupture community that proof hurts badly. It's a really stupid idea. There are other practitioners that say if you prove it, it lasts forever. Our experiment established it looks like the latter, not the former. But in my engineer's analysis of proof and step, he couldn't explain the data at all. He was just waving his hands. So that's when I knew we were going to have a fight. Because I was not going to allow him to analyze the data the way he wanted to. I'm too distinguished and member of the team to allow that to happen. However, I then learned that left censoring is not naive, it's just wrong, particularly in this case. So then suddenly the case became much more urgent. That was 3 years ago. We're still trying to get this all unwound. It's been interesting, it's been successful for the most part. The team recommendations are all following my analysis. The team lead actually split me off and the principal engineer off from each other, off from that team. So the splinter team is the rest of the team. They interact with one or the other of us. And it's the result because it's complicated. He says everything I'm doing is wrong, and I can prove everything he's doing is factually incorrect. It's not fun. And ultimately, the team has decided to go with my recommendations, which is cool. But we're keys to this persistence. Doesn't hurt my reputation in the field, frankly. The team lead knew that. Graphical presentations, which is why I've tried to use a lot of graphs today. The engineers understand the graphs, they don't understand the math. Oh, and by the way, I've got formal proofs, which have proved helpful, but they don't help me with the real problem children. They don't understand. They don't understand the concept and a proof of what happens when you cross the equal sign. That immediately invalidates the proof. Because everything they want to do is, oh, I'm just going to assume it's true. Well, you just assume what you're trying to prove. Sorry, that's an F. Okay? So I'm glad I had a chance to share this. I would love for questions. If you want to talk about it the rest of the time I'm here. If you want to learn about proof and step, I'm happy to talk to you about that. But this has been fun, and I just thought it'd be interesting. Not many people are aware of Weibull regression and dealing with censoring. So I thought this might be interesting for people here at university. With that, thank you. I've had fun. I hope I haven't bored you today. Okay.
That is possible to consider just one likelihood. A mix two parameter level, parameter weight, so we can without having to separate our parts.
Yeah, but the problem is they really are two separate parts. I mean, the issue is coming back to the measurement of time. And you see, the way I'm doing it, this is the actual plot that I'm dealing with because we're dealing with load here. And I have time over here. So I don't even have a polyrated there. And that's actually how I'm framing it when I do the derivatives for all these things. I highlight that distinction. So it really comes back to that conditional argument that the only way I can get to here is to survive here. So it's not like I'm dealing with competing risk. There's a section where this has got to be the risk, and then it moves to a new risk. Is that helping, Andre?
It does. But the way I think is to have a structural change throughout time. Extra parameters that we have, depending on the 730 data points that you have a different 730 points, it would be a little bit different threshold.
But here it's defined by the moment it got to the hold condition. So I can identify the ramp time from the hold time. So the threshold is not moving, it's well defined. It was the moment that it achieved the load. Correct, didn't matter what the previous time was. That literally was the definition. Now, there was a little bit of variability in it, but there was nothing that we worried about. And the fact that the way we created the times was deterministic. So that's the difference. I mean, I agree with you that if there was a threshold that you needed to estimate, that makes perfect sense.
Not the case.
But not in this case. It's well defined. And in fact, that's how we collected the data.
So you have a physical explanation for that.
Yes.
It's solved.
It is.
It is not an issue.
No. Now, is it clean? How it makes that transition is a little bit of a curve. We were sampling at 100 hertz, so 100 times a second. We have those plots, and the team made the decision at what point it achieved threshold. But it wasn't estimated, it was, this is what we look. And if we had seen issues with outliers with the very early failures, that would have suggested us to go back and look at how we define time zero. Is that fair enough?
Yes.
And it was set up that way, but we saw no issues with the modeling with the very early failures. They were all being well explained by the model. But that would have been an alarm to go back and investigate. And it could either be an outlier or it could have been that we just did not define zero properly for that one. And, you know, there was a judgment call, but that was something that we have documented thoroughly in the database. That make sense?
Thank you.
Oh, this database is so documented. It's not perfectly documented, but we came as close as we could.
No more questions.
That's good. I'm happy.
Thank you once more.
Thank you for putting up with it.
Obrigada a todos que nos acompanharam até aqui nessa série de seminários. Boa tarde.